Okay, good morning. Good morning. Um, okay, today we are going to take a very, very important unit, maybe the most important unit in the entire courses. I'm not exaggerated the importance of this unit because we are talking about decision, right? And that is the major purpose why we learn business analytics, right? You want to why do you want to do analysis? Because you want to make business decision, right? Why making business decision is difficult? Because you have uncertainty in front of you. You want to make decision under that uncertainty, right? So what a probabilistic model can do for you is that, well, that model cannot eliminate the uncertainty. Uncertainty is still there, but it gives you a way to estimate the uncertainty, right? To assess the uncertainty, so that you can make a optimum decision, which means you can make a decision with the maximum expected value under uncertainty, right? And that is the most important thing that we want to do in business analytics, isn't it? Right? So this is virtually the most important unit in the entire courses. Last week our homework is to do the MIT online courses, right? So first thing I want to do is like, do you have any question about the courses? Any question? Any comment? Yeah.
Was it based on a different version of RStudio or?
Actually, they are not using RStudio. They are using the primary art interface. So that interface is kind of like kind of old, right? It's not as convenient as in RStudio. So RStudio is actually you're still using our language, but it give you a lot of tools so that programming is easier, right? When you want to check the data object, you want to check the structure of data object. When you want to run the notebook, it's easier to make it in RStudio. Okay, so MIT is still using the primitive interface of R. Okay. Any more question? Anything that you feel that it's difficult to understand in the course? So compare with the way that we are teaching, right? You can see that the MIT course is more intensive, right? Because you only look into one of the unit when they explain the logistic regression, right? It's just one of the 4 or 5 unit there. So in a week they will have like 4 or 5 type of unit like that. So see, actually in the mainstream business school, the way they teach business analytic is a lot more intensive than what we do in here, right? So you might feel like I'm pushing too much to you guys, but actually it's not the case, right? I already reduced the reduced the intensity a lot. That's the first thing that I want you to experience, right? And the second thing is that you may see that they are still involved a lot of mathematics, isn't it? Right? The assistant professor it's kind of a female professor, right? He explained a lot about the mathematical detail. I know that mathematics could be difficult for some of you, but don't worry about that because all of the mathematical detail has been encapsulated in the R functions. Okay, so it's not if our purpose is just only to to estimate the probability, right? To predict the outcome, then what you need to do is the function call, right? You have a function call to make the model. You have a function call to make to estimate the probability, and from the estimated probability, you can predict the outcome, right? That process is pretty much already encapsulated in our functions. So when we do business analytics in the application level, you don't really need to know too much about the mathematics. That say, I don't mean that math is not important, right? If your purpose is to like, if you want to um, validate the accuracy of each of the individual coefficient, right? If you care about if you want to confirm the relationship between each individual predictor, each individual predicting variable, and your outcome variable, right? If you want to make sure that the effect on the predictor are significant to the outcome prediction, there are lot of work to do, right? And I told you several times, I cannot cover that in our course. So our course is actually, today we are going to pull back to the application label, right? Using the tool that already given in the R environment, okay? We basically we are going to do something like this. Basically, we are going to do something like this, right? We want to not only make the prediction, but also do the decision, okay? Okay? So, prediction is easy, but there is a process from prediction is to decision, and that is what we want to cover this week, okay? Now, before we go any further, let's take a look at this week's material. Now we are in Unit 11, right? Unit 11. So you go to the, sorry, this is wrong. This should be Unit 11, okay? You go to this folder. There are two things, right? So this is there's a PowerPoint, it's a zip file, and if you unzip the file, you should have a folder called 11 decision, right? So put the folder like this, if you're okay, okay? Now, before I go into the decision process, that's kind of like reviewed a little bit, right? Okay. So this is what we call predicting modeling, right? We have data, and usually in the data you have an outcome variable, the variable that you want to predict, right? And you have some predicting variable. Okay, unfortunately, there are a lot of different names, right? The predicting variable is also called factor, predicting variable, regressor, predictor, independent variable. There are a lot of different names, but they're talking about the same thing, right? So outcome, there's sometimes called outcome response, target variable, dependent variable, DP, things like that. But whatsoever you start from data, right? And within the data, there is an outcome variable, right? So you make a model out of this data, and then you use the model to predict the new data, right? So usually you have some data, and in this data, in this training data, you need to have X, you need to have Y, right? And then you have X, then you can predict Y by the X via the model, right? That's basic the way it works, right? And we learn two types of model, right? One type of model is for numeric variable. That is linear regression, isn't it? Okay. Uh, the way it works is that the model is nothing but a linear combination of the predicting variable, right? You use a linear combination of the predicting variable to predict the value of y, right? That's one way to do things, okay? And the other way to do it is when your y is a categorical variable, right? Especially in most of the in a lot of the business scenario, your y is actually a binary outcome, right? Like you want to predict whether a customer will buy from you or not next month. Okay, that's that's a way that we want to predict, right? If we want to actually in our final presentation, we want to predict for the Tafang retail store, right? We want to make a model to predict whether a customer will buy from us in the next period. Sometimes we call this repurchase probability, okay? So we want for each of the customer, I want to know his repurchase probability, and I also want to know his expected buying amount, isn't it? Right? So what is the model should I use if I want to predict the customer's repurchase probability? We learned two models, right? Linear regression, logistic regression. So which model should I use? Which method should I use to predict the probability of repurchase? Should I use linear regression? Should I use logistic regression? Yeah, why? Because logistic regression is to deal with the binary outcome, right? And when you have an outcome of binary outcome, you're actually predicting the outcome of y equal to 1, right? Binary outcome usually was encoded as 1 or 0, right? And in the Tafang case, by y equal to 1 when I told you we have data, right? So when y equal to 1, it means that the customer buy in that period, right? If you do not buy, the y equal to 0, right? So that's basically the case. But when you are predicting probability, things are a little bit complicated, right? Still, you are using a linear combination of linear combination of x, right? But you cannot predict because so now you don't want to predict y, right? You want to predict the probability of y equal to 1, isn't it, right? And this linear combination cannot predict that probability directly. There are some mathematical complexity between them, right? And I told you that this mathematical complexity is already encapsulated in the R function. So if you just want to use x to predict y, predict the probability of y equal to 1, it's just call the function, okay? That's not, so making prediction is not too difficult. How to use the prediction to make business decision is what we want to learn, right? As a manager, it's what we want to learn to do it, right? Okay. Actually, in some business scenario, you can hire engineer to build model for you, right? So, for example, if you have a lot of data, right? You have like 20 million customer, right? And each customer you have like 500 predicting variable. In order to do that, a manager maybe do not have the ability to do the model by himself. Right? So he can hire an engineer to do that model for him. But as long as the model is there, you actually can use a simple function code to make prediction. Just treat the model as a black box, right? So it's just a tool to help you make the decision. Think it that way. That the engineer can make the model for you, but he cannot make the business decision for you. To make a business decision, you need to combine your business logic. You need to combine your domain knowledge, okay, with that prediction in order to make good decision, right? As we say that building model and making prediction is easy, right? It's quite straightforward. To fit the model, you need the data, right? And then you put the data and you specify the outcome and predicting variable, right? And you call GRM. Okay, remember to put family and binomial. That is the way to build logistic regression model with the GRM method, right? GRM is a method, it's not a model, okay? You can build a lot of different models by GRM. Logistic is one of it, okay? When you want to make logistic model with GRM method, you need to specify family equal to binomial, right? Okay, and after calling GRM, you get the model, right? You can see the model summary, okay? And then you can use the model to do prediction, right? If you want to predict the training model, okay, then you can basically just give it the model and co-predict, okay? Remember to use type equal to response, okay? When you're predicting probability using logistic model, you always need to include this type equal to response, okay? So if you do not give it new data, it will just predict the training data, okay? If you want to predict new data, then you need to provide a new predicting variable, and according to the new predicting variable, it will give you a new set of probability. Yes?
Professor, for the top on the data, will we have a training data or just read?
That is the thing that I want to explain next week, okay? All right? This week we were still using the diabetics data set to explain how to make decision from prediction. This is what we want to do this week, okay? So next week, I will go into the Tafang data set. I will tell you how to prepare the data to make the model and make the decision, okay? Okay, so this is kind of like a review, right? Okay. So up to this point, it should be very straightforward, right? What's difficult for logistic model is actually the model accuracy measurement, right? It's kind of confusing, right? When the MIT course start to explain the ROC curve, that it's pretty confused, right? Because there are a lot of jargon, a lot of terminologies, right? Okay. As I told you, don't try to remember the definition of all these definitions. It's not really necessary to do good decision. What's important is you need to figure out what is the confusion matrix, okay? And as long as you know the confusion matrix, then as long as you know that confusion matrix, then you can actually like just put into this mathematical formula, then you can calculate all of this accuracy metrics, isn't it? Right? Okay. And there are two types of accuracy metrics, right? One type of it is they say the preset threshold, right? In order to have that, in order to have this matrix, let me say it again. If you want to have this confusion matrix, only the prediction is not enough, right? Because the prediction only give you a probability for each data point, right? After you make the prediction, right? For each data point, there is a predicted probability, isn't it? Right? And how can you transfer that probability into the prediction? The outcome is 0 and 1, right? The probability is a value from 0 to 1, right? So you need a threshold, right? You need a threshold. So usually, traditionally, the threshold was set at 0.5, okay? When you set the threshold at 0.5, now this is the prediction, right? This is the prediction. Now the color, it means because you say you have a training data or testing data, you already know that actually that data point y equal to 0, y equal to 1, right? Because you are in the training data or in the testing data, right? So you know the y, the actual value of y. And the actual value of y is not a probability. The actual value of y can only be 0 or 1, isn't it? Okay? So they are only two alternative of the actual value of y, right? Okay. However, your prediction is a value, right? So if we plot the distribution of the predicted probability, okay, this is the plot of the distribution of predicted probability for actual equal to 0 and actual equal to 1. Okay, so this chart is actually very important, right? It's more traditionally, actually also in the MIT course, they kind of skip this point and jump to the ROC curve directly, right? Okay. But actually, in order to understand what is the confusion matrix, you need to know this, right? Right? The first thing you want to do is after making decision, this is the information that you get out of the prediction, right? After you get the prediction, you know the distribution of probability for the data point of y actually equal to 0. This is the green histogram, right? And the red histogram is the distribution of predicted probability of the data point that y equal to 1, right? So you plot them together, right? And then you need a cutoff, right? If you have a cutoff here at 0.5, then you will have 14 points, right? This 14 point is it means that we have 14 points, the predicted probability is larger than 0.5, okay? And some of them, they are actually 1, isn't it? And some of them, they are actually 0, okay? So when you set the threshold here, you actually predict that this 14 point, the outcome is 1. Well, but some of them is actually 1, some of them are not, right? Okay. Likewise, you are predicting 85 point, y equal to 0, but some of them they are actually 0, and some of them they are actually not, right? And this make up the TN, FN, FP, TP. They make up this 4 value, right? And that 4 value jointly is what we means by confusion matrix, right? So let's say it means that the confusion matrix would change when the threshold move, isn't it? Right? When the threshold move up, this value will decrease, and this value will increase, right? When the threshold decrease, it will actually increase the positive prediction, the number of positive prediction, and decrease the number of negative prediction, isn't it? Right? So that is the. As I told you, don't try to remember these things. Okay, try to start from this point. If you want to make good business decision, this is where you want to get started. Okay. Rather than looking into the RC curve, that type of things. Okay. See. So let's do some exercise. Actually, today I want to kind of review what we have learned in logistic regression, because that concept is important. Okay, and before you know that concept, before you can fully understand that concept, you cannot make good decision out of the logistic regression. Okay, so this is important, right? This is the result of prediction. Okay, and only from the result of prediction you actually cannot have a confusion matrix. Okay, you need to set a threshold. Okay, the problem is that when the threshold change, the contents of confusion matrix also change. Okay, that is the thing that make things complicated. Okay, so we actually let's try to jump into the real case. It would be a lot easier. So this is the MIT case that we have done last week, right? So we want to build a model that estimates the quality of care, right? So how does the data come from? They actually have a sample of a very, very small sample, actually. It's 131 points, right? And then they kind of make a model out of it, right? But the sample data only have the medical record, right? How can they acquire in the MIT course, how do they acquire the outcome variable? Where is the outcome variable come from? So you are a medical insurance company, so you have the medical records, medication record of each of your customer, right? Each of the patient. But how do you know that they are good care, or which one is good care, which one is bad care?
Experts judge the experiences.
Good. Do you hear him? Okay. They hire experts to do the labeling, right? So they sample the data and they label the data. And as long as you label the data, you have X and Y, and you can build a model. Okay? And then they build a model. So they have a logistic regression function that for all of the other maybe millions, tens of millions of diabetes patients, they can use this model to predict, to estimate their probability of poor care, right? Isn't it? That's basically what they are doing. See, thing like that. You label it by expert labeling, then make the model, and then you have the data, you make prediction. Okay. Now, let's have some. Up to this point, this is basically what we have already learned, right? I want to make sure that you already capture this concept. Let's do a quick quiz, right? So, raise your hand, right? What is the sensibility of confusion matrix 1? Who has the answer? what is sensibility? You actually can. Sensibility is actually talking about this, right? Given given that actual is 1, right? What is the probability that I will predict it as 1? Let me say it again. Sensibility is talking about actual 1, right? Given that actual is 1, what is the probability that I will predict it as 1? That's called sensitive, right? So how much is the sensibility? Yeah, it's 80%, right? It's 80%. It's 5/25, isn't it? Okay. So what is the specificity of confusion metric? What? How many? Is that 40? Yeah, it should be 60, right? It's 15/25, right? So it's, specificity is that given that actual is 0, what is the probability that will predict 0? Isn't it? Right? Okay. So this is sensibility specificity. Then, if the metric jump from to go from confusion metric 1 to confusion metric 2, did we increase or decrease the threshold? Increases? Why do you say that they are increased? Is increasing the right answer? Think it again. If you increase the threshold, okay, the number of positive would increase or decrease? Sorry?
If we increase the threshold value, then the number of positives will increase.
The number of positive would increase. Think about this. If you increase the threshold, the number of positive would decrease, right? So in this case, the number of positive are decreasing, right? So they are increasing the threshold, isn't it? Right? That is the logic, right? Okay. And RC is the traditional way that we use to make decision, but it is really not a good way. Okay. Today I'll give you a better way to make business decision, right? See, the RC is actually one to it's one to visualize the trade-off between specificity and sensibility. Okay, let's see. In our folder this week, we have this EN DPP sim that R. Okay, so let's run. We have played with this last week, right? Okay, so if you put the threshold, this is the simulator, right? So you can set the threshold as you wish, right? as you see that when I move the threshold will move with. So if I set the threshold to 1, if I set the threshold to 1, I basically predict every point as 0, right? Because everything is below the threshold, so everything will be predicted as y equal to 0, right? So in that case, the specificity would always be 1, right? Because if you are 0, then I will always tell you 0, because everyone I'll tell them are 0, right? Sensibility is very high, but actually, sorry, specificity is very high, but sensibility is 0, right? Okay? So another extreme, if I set the threshold to 0, you can see the point jump to here, right? Okay? So here we have the sensibility 0, and then we have the specificity 0 and sensibility equal to 1, right? And sometimes you need to have a threshold, right? In some business scenario, sensibility is more important, and in the other business scenario, sensibility is more important, right? Okay, so so in different business contexts, the threshold need to change to reflect, to fit into your business condition, isn't it? Right? So in reality, the threshold is not fixed, right? You need to have a trade-off between the two, right? So this ROC curve is kind of like visualize the trade-off between sensibility and specificity, and that trade-off can be achieved, can be adjusted or manipulated by manipulating the threshold value, isn't it? Right? Think about the real case. Now you are in a medical insurance company, okay? So if you want to take action on some of the poor care patients, right, you need to determine, you know their probability of poor care, right? So you need to know the threshold. Maybe like the threshold is higher than 90%, then I take action, okay? Maybe your decision is like the threshold is higher than 70%, then I take action, right? So the threshold of making decision is not the same as the threshold of making prediction, right? When you are making decision, the best threshold is usually 0.5, right? Because if you are looking for like accuracy, isn't it? If a point's probability is larger than 0.5, right, it's more likely that its y is 1, right? Isn't it? Okay? If a data point, the probability is lower than 0.5, then it's more likely that that data point's y is 0, isn't it? Okay? So when you are making decision, it's kind of like the threshold is fixed at 0.5. Okay? But when you are making decision, the situation is different, right? Okay, you need to think about your business scenario and try to make a threshold. You need to adjust the threshold you need to find the optimum threshold for maximum expected value, right? That is the thing that we need to learn this week, okay? Any question so far? I just want to like kind of warm up and bring you back to the basics that so we can see the example better. Okay. Now let's look into the notebook. Okay. Let's start to do the things. Okay. take 11A first. So first chunk is like, as usual, as you can see that I split the data, right, for training and testing, and then I build the model and see the model summary, right, and then let's do it here. Remember to set the working directory, so, and run the first call. Then this one. Now we already have the summary, right? In summary, they are coefficient. And as I say that, for now we don't have to worry too much about the coefficient, because we don't really care about the individual coefficient. We just want to use the coefficient to make prediction for us, right? And if that is the purpose, you don't really need to care about this coefficient too much. And then you can do the prediction, right? So for training data, as I say, for training data, you don't need to give him new data, right? Just give it the model and say type equal to response. Call predict, then you get the prediction, okay? So check here. After I run this, sorry, what is the problem here? Okay. He's complaining that I do not have enough margin to do the plot. Okay, say margin too large, so it's I do not have enough space, which that's what he say. Okay, now we have the plot. Okay. So what I have done here is like I do the prediction, right? And because the training data has 99 point, right? So I have 99 probability. Is that okay? I have 99 probability, and I draw the 99 probability in a histogram. Then I see the distribution of predicted probability. And then I set the threshold at 0.5. Okay? Then I get the confusion metric. I can calculate the accuracy metrics, the accuracy measurements, right? That's for training data. Okay? So I see. Actually, I do a confusion metric this way, right? Confusion metric is nothing but the actual value and the prediction value, right? The actual value is here, right? It's already in the data set. The predicted value, in addition to the predicted probability, you need to set the threshold, right? So predict is like predicted probability larger than 0.5. So now you have the confusion metric like this. See that? Okay? This is the predict, this is the actual. Okay. Now we want to like now you have the confusion metric. You want to calculate the value of this thing, right? So I basically just put this mathematical formula in R, right? So I define a function called accuracy matrix, and the input is actually the confusion matrix, okay? And the 3 is actually just to run, just to like specify the number of digit after the decimal point. Okay. So this is quite straightforward, isn't it? Right, in R. I think that the way that I do it is better than the way the MIT do it in the course because they are kind of like um, kind of jumpy, kind of choppy. And that is what training, right? Again, in training, I only have like, I put the prediction of training data in Pret 2, okay? So Pret 2 is a vector of length 32, uh, which is the number of data point in the testing data set, right? Get it? Okay. So again, I can see the confusion metric 2, and then I can. If you still remember the S apply function, okay, this is a very handy way to use S apply, right? Now I have two confusion metric, one for training, the other one for testing, right? And I want to apply this function to these two confusion metrics. And then, as you can see that the outcome is very nice, right? You can very nicely compare the two, okay? So in this case, as you can see that the accuracy metric for testing and for training, they are basically quite similar, right? So this is the good thing, right? Sometimes if the accuracy of the testing data is worse, is much worse than the training data, then it means that you have problem in your training and testing data. Usually it means that when you separate the testing data, the distribution inside the testing data is different from that of the training data, right? And you need to split it again and try to make that, to make it correct, okay? Okay, so it's 10 o'clock. Let's take a break and we'll be back at 10 after 10, okay? 喂喂。